All righty. That was Hulk, everybody. Give it up for Hulk. Bruce Banner, also known as Bruce Banner. He got into some interesting experiments, and things didn't go as he planned, but it kind of worked out in the end. The world got a superhero. All right, anyway, I digress. Actually, can you digress if you start off topic? Anyway, let's talk about the rest of the semester. What's left? We have, by the way, can you guys hear me okay? I'm trying these new headphones.
Yeah.
Good? Okay, good. This is what happened to my trusty old headphone earbuds.
Oh boy.
Yeah, I was gonna tape them. Actually, the whole semester I've just been taping them, but I figured, maybe I'll try something else. And I'm glad you can hear me. Okay, so we don't have that many days left. I don't know if you noticed, but today is May the 4th, and it's a special day for a lot of Star Wars people. They'll greet each other. May the 4th be with you. And we are done, wait a minute, next Tuesday, right? And what that means is that we have class today, just going over some of the stuff we learned last week. We did a real super quick treatment of the Sierpinski triangle as well as the Cook curve. So we're going to focus on those today. Those will be on the second test, or at least one of them. And next time we're going to go over a set of review problems, and that one's actually already posted on our Blackboard page, but I can also send it to you on email. And so that's something you should do before Thursday. You should work on those practice problems before Thursday. So we'll go over them, and I feel like anytime a review is coming up, it's always a good idea to do the problems beforehand, because you're going to learn better. You're going to learn more. You're going to get more out of it. And then next Tuesday is our second test. And the second test will be conducted very much the same way we did the first test. So I'll ask you to have your cameras on the whole time. And the test is going to be similar. It'll be on Blackboard. And yeah, remember I sent you a Zoom link, and we're going to do it the same way. Basically, you come into Zoom. I'm going to give you a password for the Blackboard test so that I'll get everybody's attention on Zoom, and then you're going to do the test, and that'll be it. Now, May 17th is the final day to submit late submissions. If you've skipped an assignment, one of those projects, or if you don't have 10 out of 10 for it. I mean, if you've submitted something late, then that's 7 out of 10, that's maximum. But if you've had points deducted, and I just realized I didn't finish grading all the Celtic knots. Some of you have a grade for the Celtic knots, but some of you don't. I'll do that. I'll finish that by tonight. So you'll have still almost 2 weeks to turn in any late ones or resubmissions. So that's May 17th. We can say midnight on May 17th. Okay, so that's what's going on for the rest of the semester. It's just basically today, and then Thursday, and then next Tuesday. So 3 days of class, and then you have one more deadline, which you don't have to worry about if you've turned everything in on time and you've got full score on everything. But if you do want to resubmit anything, then May 17th, midnight is the time. All right, any questions? Everybody good? Okay, so let me share something with you. I'm going to try to see what I could do with this Blackboard, the Blackboard whiteboard. But because I don't have the eraser, I may not be able to do everything that I want to do. But let's just see how it goes. Okay, so let's start with the Cook curve, shall we? And just like with all these fractals, it's a stepwise process. It's an iterative process. So each step is an iteration. That means you kind of go back and do the same thing over and over and over, right? So each time you do it, it's called an iteration. By the way, if anybody ever says, "Oh, let me reiterate," you don't have to say that. That's really, that's really beating a dead horse. That's not a nice way to put it, but anyway, it's unnecessary to say reiterate. You can just say iterate. Let me iterate, because that means going back and doing the same thing. So step 0 in this case is just a straight line. So we start with a straight line. Now, going from step 0 to step 1 is going to define the whole thing for us, because after that, you're basically just going to repeat, rinse and repeat. That's the kind of thing this is. So, yeah, Sophia, what's up?
Hi, Professor. I'm so sorry,
Yeah.
but Ria has been having connection issues all day, and she just wanted me to let you know that she's trying to log into class, but her internet's just not letting her.
Oh man, her internet. I thought we all share the internet. No, I know. It's connection, right?
Yeah,
Her
her
connection.
connection, sorry.
Yes, it's okay. I'm hoping that she'll get in, but if not, then she will just, I guess, just have to watch the recording, which, all of these lessons have been recorded. So if you ever did miss anything, or, you want to check on something, you can just go to that lessons folder or lessons table of contents, and you click on the recordings and you can go back to any of them. Okay, so anyways,
I'll let her know. Thank you.
Thank you. So step 1, what we do is we take, and this is kind of hard to draw without the eraser, but I'll try. So we're basically going to take out the middle third of that straight line, and it's like we're going to pitch a tent right here in the middle, like that. Ria's here. What's up?
Hi, Professor. Sorry I'm late. My internet just was not connecting to my laptop.
It's okay. It's okay. I'm glad all your machines are finally talking.
Me too.
We're good. We're good. Don't worry. We're just getting started. All you missed was a angry episode from our friend Hulk. So, anyways, step 2 with the Cook curve, and you might have guessed it already. We're going to take each of these straight line segments, and there's 1, 2, 3, 4 of them, and we're going to do the same thing. So we're going to go back and do the same modification that we did going from step 0 to step 1. We're going to do it to each of these straight line segments. So we're going to do the same thing that we did once. We're going to do that 4 times. So let's see if I can do it here. Just drawing very short lines. Oh, I'm already off. I know. Sorry. Okay, whoops. And I don't have an undo or eraser, so this is just a one-time deal here. Now, all these little line segments that I'm drawing or trying to draw, they're all of the same length. Remember that my original modification was to take out the middle third and then do these extra segments. Well, you could think of it as one of them being extra, and the other one is the middle third that you took out. You just kind of fold it up. And in just a little bit, I'm going to show you some animations online. You know, they can illustrate this drawing process a lot better than I can here. But anyway, so step 0, a straight line. Step 1 has just that triangle in the middle. Step 2 has 1, 2, 3, 4 little bumps. These little bumps right here, one drawn to each of the shorter line segments here in step 1. And then step 3, you would just do it, the bumping process. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times. So that's the Cook curve. Now, sometimes you'll hear the word Cook snowflake. And if you Googled or used Ask Jeeves or what other search engines you might be using, stuff will come up on the Cook snowflake, and it's the same exact thing, except it just has 3 copies of the Cook curve. It actually looks a lot cooler. So Cook snowflake. I'll just do the step 0 here. You start with an equilateral triangle, and then, so this would be step 0, and then step 1 would be where you draw the middle bump to each side like this. Now, again, I don't have an eraser, so you would take out these lines here, and that's actually called a hexagram. And then, so that would be step 1, and then step 2, you keep doing it just like we did in the Cook curve. Now here at this juncture, I'm going to show you a little video, and let's see if I already know that I can't get sound, so it's going to be a little bit unfortunate, but I picked a video that doesn't necessarily need sound. It's just 2 minutes long, so let's go ahead and watch a little thing. And this is actually on the Cook snowflake, but just understand that Cook curve is just 1/3 of Cook snowflake. So let me rewind this. And you're going to get information on the area of this thing as well as the perimeter. Now with the Cook snowflake or the Cook curve, our class is actually not going to do anything with the area. It's we could, but it's just getting to a level of tedium that I don't think is necessary. It turns out that the area doesn't really grow that much, but the perimeter goes to infinity. Okay, so anyway, so here we go. I know you can't hear the sound, so maybe I'll do some play-by-play. Let's see. So the area doesn't increase that much. There's a limit. There's a limit to the area. The 1.6. Does that sound familiar? 1.6.
Do you want to clean the bathtub and make money? Do you want to come help me spray?
Okay, so what did we just learn? We learned that the area of the Cook snowflake is bounded. It doesn't blow up, but the perimeter does blow up. And what does that mean, blowing up? Let me talk about that a little bit more. And I'm just going to now focus on the Cook curve just for simplicity. So let me go back to the Cook curve. Step 0. Step 1. So let me work with just these two for now. And then I can apply what I'm learning here to later steps. So let's assume this line segment has length 1. Okay. So our original line segment, just for simplicity, has length 1. Now it could be a 100 or something like that, easy. But like if I was going to ask you questions about the Cook curve and the perimeter or the length of it, I wouldn't make it like 7 or 55 or anything like that. I would make it either 1 or 100. So the length of step 0 is 1. Now what happens when we're moving to step 1, I'm sorry. So what we're doing actually was cutting out the middle, but then the middle third, but then we're kind of bumping that up and then adding one line. So this side and all of these sides have a length 1/3. So notice that there's an extra 1/3 here. See, at step 0, I'm going to draw these lines here. Maybe this will help. So what we did to go to step 1 is we eliminate the middle third and then just put 2 lines of length 1/3 in the middle. So then we have 1/3, 1/3, 1/3, 1/3. So the length here would then be 4 times 1/3, or of course 4/3. right? Is everybody okay with this? If this has length 1, then step 1 has length 4/3, because we're adding an extra line of length 1/3. Okay, let me go to the next step. So this would be step 2, and this is beginning to be much harder to draw with my method anyway. Now, how long is each line going to be here? Each of these little lines. Anybody help me? 1/9. Yes, perfect. Minjung, thank you. So each of these little guys is going to be 1/9, because notice that our starting point now was 1/3, and then we cut that into thirds, bump up the middle, and add an extra line. But each of these is length 1/3 of a third, right? So I'll put a little thing here. So this is 1/3 of 1/3, which is 1/3 times 1/3. Which of course is 1/9. So each of these little guys is 1/9. Now, how many do we have? I just counted it for you, actually. Yeah, 16 of them. So 16 nines. I have 16 pieces that are each 1/9. Now, there's a pattern here, of course. It'd be really hard to study something like this if there wasn't a pattern, but there's a pretty nice and easy pattern here. So each step, can somebody actually tell me what's the how can I calculate the length of, let's say, step 3? And do I have to draw the picture?
Probably not. Would you multiply it by 4/3 maybe?
Ding,
Or
ding,
by
ding, ding,
itself?
ding, 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 ding. Yes, 4/3. So I don't necessarily have to draw it, because if I know the previous step, like step 2, I can get the step, the length of the next step by multiplying by a factor of 4/3. That's the, I guess you could call it a growth factor, or a factor of increase. So the initial has length 1, and then after that, each step grows by 1/3. And then that, of course, that growth compounds, if you will. But there's a real easy way to calculate the length of any step, and it has that factor of 4/3 in there. We could think of step 0 as being of length 4/3 to the 0. So that's 1, by the way, if you don't remember. Anything raised to the 0th power is 1. And see how simply this comes. Every step is of length 4/3 to the and number of the step. I'm really just kind of spelling it out for you here. I think you could have figured this stuff out, but figured I'll show you once. So if let's say I was interested in step 5. What is the length of the Cook curve at step 5? Length of Cook curve at step 5. So this would be 4/3 to what power? 15? What should I raise it to? That's too easy. 5, of course. And then I can actually calculate that. Now, all you guys have your calculators, and you can calculate what this would actually be. So 4/3 to the 5th power. Might be a good idea to learn how to use that. Use your calculator there. I'm getting it. Let's do an approximation of 4.21. And every step after that will just be multiplied by 4/3, 1/3. So each time you're just increasing the perimeter by 1/3. And you can see, this doesn't take some kind of higher level math to realize that growth never stops. Even when it reaches 1,000, next step is going to be, 1,300 plus. When it reaches 1,000,000, next step is going to be more than 1,000,000. So it just keeps on growing with every step. And these fractals, you could think of them as being kind of infinite creatures, if you will, that you could theoretically go as many steps into it as you want. Now, as far as you drawing, I think step 3 would be the last one I would ever expect you. Maybe even step 2. What problem did I give you to think about over the weekend? Was it step 2 or was it step 3? Anybody remember? I draw the Cook curve to step 3. What is the length of step 3 if step 0 has length 1? Okay, so step 3 was the homework, and if you draw it pretty big, if you start drawing fairly big, you could do step 3. It's very hard for me to do with this program, but you could do it by hand. And the length of it, though, what did you get? The length of the Cook curve at step 3. So it'd be 4 cubed divided by 3 cubed. What would that be? Someone with a calculator. I know it can be hard to access calculators these days. It's like you need some kind of special device. Well, I guess I'll leave that for your next homework then. Let's move on to the Sierpinski gasket. Now, sometimes you'll hear it being called by the word Sierpinski triangle, and it doesn't matter. Either one's fine. Sierpinski. I like gasket. Because I could blow a gasket and it sounds cool, but blowing a triangle, I don't even know what that means. Sierpinski gasket. Now, it's called a gasket because basically it's a two-dimensional thing, but then you start taking parts out, so it ends up being this real very much a broken piece of material. And if you know what a gasket is, like in an engine, they're basically they keep the oil from dripping out. They're basically there to insulate connections. Anyway, that's besides the point. Let me draw a triangle, and it's nice to start with an equilateral triangle, but you could actually do this with any. So this is our step 0. Step 0. It's actually the same step 0 that you would have in the Cook snowflake. By the way, Mr. Cook was actually a Swedish mathematician, and it's not a real common name, but anyway, Cook. And then Sierpinski was a Polish mathematician. These are all of European origin. Okay, so Sierpinski gasket, the way you draw it is you take the midpoint of each of these sides. Then let me go ahead and draw my step 1 here. So the outside of this thing doesn't actually change. You're still looking at that equilateral triangle. We're going to connect the midpoints like this, and then we're going to erase this middle piece. So I'm just going to make it black, as if that's now negative space. Oh, that's annoying. So basically we're subtracting area. Okay, does that make sense? So we're taking out, I guess you could think of it as the central triangle. So by connecting the midpoints, what you're making is you're making 4 triangles out of the big triangle, right? And then you're taking out the middle third. So can somebody tell me that if the area of the original is 1, what would the area of the step 1 set of 3 triangles be?
Professor, can you repeat the question?
Yes, so if the original has area 1, then what would this step 1 have as area? See, I divided it into 4 equal parts. and I'm taking one out. Three-fourths, thank you. Yes, 3/4. So step 0, area 1. Step 1 has a quarter less. Okay, so this has area 3/4. And guess what? The next one, and this is again an infinite process. If you want to take it all the way, you will never be done. So to some degree, we have to live with an unfinished product. I'm going to make this a little bit bigger. So I'm going to take out the middle third here. Drawing each step, basically you have to draw the previous step first. So now I would take out the central triangle of each of the triangles in step 1, like this. And then I'll do the subtraction by just coloring them in. I'll try to be a little bit quicker here. So I'm taking out all these central triangles. I know it's not pretty, but it'll have to do. Okay, so what do you think the area of this guy would be? (12/4). Well, let's see. Area would be the previous one, basically 3/4 of the previous one. So this would be 9/16. 9/16. You guys remember how to multiply fractions? You multiply across the top and the bottom. So you don't need that common denominator or anything like that. When you're multiplying fractions, you just do the top and the bottom. 3 times 3 is 9. 4 times 4 is 16. Now, you could probably take it from here, right? So each time you go up a step, you will lose a quarter of the area. So you're left with 3/4 of the area. Does that make sense? So we could say here in step 0 that the area is 3/4 raised to the 0th power. And here in step 1, the area would be 3/4 raised to the 1st power. So this is very convenient how this works, because you're just taking the number of the step. Like here, step 2, the area is going to be 3/4 to the 2nd power, 3/4 squared. And therefore, like, let's say, step, what should we do? Step 6, let's say, has area, you can figure this out now, 3/4 to the 6th power. And it's just a calculator exercise to actually get a number for that. I'm getting 0.18 approximately. Different calculators, you might have to press different buttons. I'm just using my iPhone, and I don't know if you can see it here, but you could use any calculator to find this kind of thing. So this way we could figure out the area of any step of the Sierpinski triangle, also known as the Sierpinski gasket. Now, what's the point? Why am I doing this? Well, this is an interesting illustration. Just like the Cook curve was, Cook curve has infinite perimeter but finite area. This one has infinite perimeter, but the area goes to 0. So if you go further and further and further, all you're left with basically is just like dust. And I want to show you a video of this guy. Somebody has prepared something nice for us. And again, I know there's no sound, but you don't really need sound. Just enjoy the visual. Oh, whoops. Oh, wait a minute. Oh, okay. Well, yeah. No, sorry. This is a little bit different. Basically, they're doing the same calculation that I just showed you. If you're wondering how to do the homework, you can look online. But I thought I was. Oh. So this is a little Fractals Zoom thing. Wait a minute. Wait a minute. Oh. Here we go. So if it feels like deja vu all over again, yeah, it is, because it's the same at all levels. You're zooming in, but it doesn't seem like anything's changing. Obviously, not all that exciting when it comes down to it, but the idea that you can just dig in, deeper and deeper and deeper, and it keeps looking the same, is really kind of a bizarre concept. But what it essentially does is it just eats up all of that area, and you're basically just kind of looking. You're left with this collection of points essentially, and there is no area in points, and that's why the area goes to 0. Okay. Anyway, what I would like for you to do is to be able to draw both the Cook curve and the Sierpinski triangle to, I would say, step 3, and then calculate the perimeter when it comes to the Cook curve, and be able to calculate the area when it comes to the Sierpinski triangle. So you don't have to do both for both, just perimeter for the Cook curve and the area for the Sierpinski triangle. And I put in, I'm going to share this homework set with you now here, and just know that this is also now available on Blackboard in the week 14 folder. But I'll just show it to you now. So there's some wallpaper patterns and some Celtic knots, and then there's some questions about the golden ratio, and then a couple questions on the fractals. And that's basically what you're responsible for. Now, I say here in the front, this set of problems may not be exactly like the set of problems on the test. Yeah, I mean, it's just the way it is. You know, practicing these will definitely help you prepare for the exam. And we're going to go over this set of problems on Thursday. Does it sound like a deal?
Sounds good.
Sound good? All right, then. I guess we'll get to finish a little early, unless you guys have questions. Anything on your mind? Anything going on that I should know about?
Professor, so is the final exam on Thursday of next week or Tuesday?
Tuesday. And
It's Tuesday. Okay.
yeah, and I'm not really even calling it a final exam because, you know, a final exam in a math class really should contain the whole semester's worth of stuff. But this particular exam is not like that. This is just for the second half. So I'm calling it exam 2. And this is like my pandemic special. I don't want to, you know, stuff is hard enough as it is.
And has the practice thing, is it already uploaded on Blackboard or?
Yes,
Okay,
it is.
thank you.
All right, so any other questions? Yes, Ria. Yeah, what's up? Ria, your hand is up.
Are we going to be going over the review next class?
Yes, that's the whole thing. Yeah, so next Thursday, we'll go over the review set of questions and set of review questions and whatever else you want to bring up. If you have any questions about specific whatever, then please bring it on Thursday. So Thursday will be the last common preparation for the second exam. The second exam again is May 11th, so that's next week, Tuesday, and that'll be the end of class. Now May 17th again is the final date to submit any late submissions or resubmissions. All right then, let me finish there, and I will see you all bright and early, 5 o'clock on Thursday.